Then first, okay, now we're recording our session. Let's move now to our presentation. So, good afternoon, everyone, and thank you for joining us. My name is Miriam Ben Kiran, and today, together with my colleague Clarice Ishmewi, we will introduce some of the fundamental concepts of watershed science. This workshop, I will focus on hydrology, how water moves throughout the environment, how we measure it, and how we use hydrological model to predict flood, drought, and support water resources management. Then Clarice will continue by introducing water quality and nutrient dynamic, explaining not only how water moves, but also how healthy that water is for our ecosystem and human. Before we begin, let me briefly introduce ourselves. Dr. Miriam Benkiran, a senior postdoc at Mohammed VI Polytechnic University, and also collaborating with MIT. My research focus on the hydrology, remote sensing, snow hydrology, and hydrological modeling. Clarice is a doctorate researcher at the University of New Hampshire, where her research focuses on water quality and watershed science. Together, we hope to give you a complete overview of how both water quantity and water quality are studied within a watershed. We would like to thank LabLinks for organizing this event and creating opportunities for researchers around the world to share knowledge and connect across many disciplines. So if you are interested about more events, you can directly go to the link of LabLinks, go to this dashboard, choose the workshop related with your file, connect, and yeah, you can sign in also to receive the weekly newsletter about the upcoming workshop and so on. It's super interesting to do that. To understand water quality, we first need to understand how water moves. We will start with the basics of hydrology, then explore how watersheds are monitored, how hydrological models work, and finally to see a real case study from Moroccan High Atlas. The first of three sessions today is about learning hydrological basis and water quality before we go to the decision making. Before talking about hydrology, let's simply observe this landscape. Water began as precipitation over the mountains. Gravity drives that water down hills where it forms rivers that transport water, sediment, and nutrients. Along its journey, this water supports agriculture, supplies city, sustains ecosystem, and eventually continues through a large river to the ocean. Hydrology is the science that helps us understand and quantify this movement. Every decision related to the water starts with understanding how water moves through the landscape. Water is continuously moving throughout Earth's system in a continuous cycle. So this figure represents a hydrological cycle that's driven by solar energy and gravity. The sun provides the energy that causes water to evaporate from the oceans, the lakes, the rivers, the soil, and the plants. As water vapor rises, it cools and condenses to form clouds. Once precipitation reaches the ground, water flows different pathways. Some across the land as a surface runoff, some infiltrate in the soil to reach the groundwater, and some taken up by the plants before returning to the atmosphere. We have just seen how water moves throughout the hydrological cycle. But once rain reaches the ground, It doesn't flow randomly. It follows the natural shape of the land. A watershed is an area where all precipitation drains through the common outlet, such as rivers, lake, or reservoir. The watershed boundaries is defined by the mountain ridges and the higher elevations. Water cannot cross these natural boundaries. Instead, the rainfall flows downhill as a runoff. Small streams merge into tributaries join the main river, and eventually all water excites through the single outlet. Because everything is connected inside a watershed, activities occurring upstream can directly affect both water quantity and water quality downstream. Now that we understand what watershed is, the next question is how do we study it? First, we measure precipitation using rain gauge. They tell us how much rain fall over the watershed, which is the main input of the hydrological system. Then, the weather station continues recording meteorological variables such as air temperature, humidity, wind speed, solar radiation. After that, we have the river gauge station. It measures the water level and the river discharge continuously. Then we have the groundwater wells that help us to understand groundwater research, aquifer condition, and the long-term availability of water resources. After that, we have satellites. So today, satellites have become the essential tool in hydrology. They provide continuous observation over a large region, including remote area where field measurements are limited or unavailable. Now that we've seen how we monitor a watershed, the next question is what exactly we do with those measurements? The hydrologist collects different types of data because no single variable can describe the entire water cycle. We measure precipitation, which is the main input. We monitor temperature, solar radiation, the wind, because they control evaporation. We observe soil moisture, the groundwater, which is represent the water storage stored below the surface. We measure river discharge, which tell us how much water is flowing through to the river. In the mountainous region, snow cover is also an important component because it stores water during winter and release it during spring. Finally, we monitor vegetation since plants um, and directly with water through evaporation. Together, those variables give us a complete picture of how watershed function. Hydrological data came from two complementary sources. The first source is the ground-based observation. These include rain gauge, weather station, river gauge station, and ground well station. They provide highly accurate measurements at specific locations and are essential for monitoring local conditions. However, they are often spare and expensive to install and to monitor, especially in remote mountains regions. The second source is satellite observation. So satellites allow us to monitor precipitation, vegetation, soil moisture, snow cover, surface water, and many other variables over very large areas with regular observation. Through satellite products usually require, although satellite products usually require calibration, validation using ground measurement. They have resolution they have like typical resolution for each product. And today, modern hydrology combines ground observation with satellite to obtain the most complete, reliable picture of water cycle. So far, we've been seeing how hydrological data are collected using field measurement and satellite observation, but observation alone cannot explain how watershed behaves. This is where hydrological modeling became essential. Hydrological model is mathematical representation of the water cycle. It combines meteorological observation, topography, land cover, soil properties, and observed stream flow. This to simulate how water moves and to store it within the watershed depends on the objective of the model, of the objective that you are studying. So we can choose the model depending of what kind of topic we want to solve and which kind of modeling we want to do and which kind of data also we have. Some model ask for many inputs data and some not. So it depends on your typical case of study. Different models have been developed depending on the objective of the study, the available data, and the spatial and temporal uh, scale of interest. Empirical models are simple. They rely on the observation relationship between variables and are used when sufficient historical data are available. Conceptual models simplify watershed process using interconnected reservoir to represent water storages and movement. They are widely used for rainfall runoff simulation. Physical-based models explicitly describe processes such as infiltration, evapotranspiration, groundwater flow, channel routing using physical equation. They are particularly used for study impact, the land use, and the climate change. Hydraulic models focus on water movement within the river channels and the fluid alpine, and they are commonly applied for fluid mapping and inundation studies. So more recently, they developed artificial intelligence and machine learning methods such as LSTM, neural network, random forest. They have become increasingly popular for stream forecasting and pattern reconstruction. So the first step is to collect observed data, including precipitation, stream flow, meteorological variable, topography, land cover, and soil information. Next, we define the model structure. We specified each pattern. This is called a model step. The model is then calibrated by adjusting the parameter. So then the simulated result matches the observation. And after the calibration, we validate the model using an independent data to ensure that it can reliably reproduce hydrological behaviors under different conditions. Once validated, the model can be used to simulate watershed process and understand how water moves through the system. It can also generate the forecast for future hydrological conditions such as river flow, floods, and drought. Finally, this result provide valuable information for the decision making, helping engineers and water management planners to reduce flood risk, allocate water resource, and adapt to climate change. Let me now show you a case of study of snowmelt hydrological modeling in the High Atlas of Morocco. Since, like, let me give you a little overview of the Moroccan High Atlas. It's located in Morocco is located in North Africa, and the High Atlas is located in the center of Morocco. So the highest elevation are represented in red here, as you can see. And this High Atlas is we call it like the what is the head of water resources of Morocco. So snowfall during winter and melt during spring. That water is used for irrigation during spring and summer, early summer. And because of climate change, this snow accumulated increased the flood uncertainty. The limited snow observation increased the uncertainty of the hydrological modeling and the flood forecasting. So the uncertainty have to be taken in consideration during our calibration or modeling process. Because It's a very important component. Then we're adding satellite products to complete what we're not able to have as a data for precipitation and so on, snow cover and so on. This is some results of a calibration. So this event happened on April 2020. We clearly see that the model that it have been used have reproduced the observed hydrograph with an excellent accuracy, capturing both the time and the magnitude of the event flow. The recession is slightly divergent, but the general overview, the calibration has been well done, and the NSO reached more than 93%. This is the validation of the same watershed. Well, this is the Tensift watershed. That one is a sub basin of Tensift, and we did the calibration, an independent validation, sorry, on that watershed. So the validation was performed on Urica, sub-basin of Tensift, using observed rainfall and discharge, recording from 2012 until 2016. Then we only took the average parameter of Tensift, the average calibration parameter. We implement directly those parameters to Urica calibration. Then we run the model to simulate the observed and the simulated flow to see if this calibration works, if the model really can validate such as the case of studies. And we found that, yeah, actually the validation reached 64%, like the NSO reached 64%, which is acceptable. And like to finalize, collecting hydrological data, it's not the final objective. The objective is transform observations into useful informations for decision making. Measurements from fields, stations, and satellites are combined in hydrological model to understand how water moves throughout watershed and to predict future conditions. These predictions support many real-world applications. They help forecast flood, monitor drought, optimize reservoir operation, improve irrigation planning, and manage water allocation, and support climate adaptation strategy against climate change. In other words, hydrology provides the scientific information needed for sustained water resource management. Then after like having this overview about the hydrology, its application, the hydrological model, the forecast analysis, and the making part, we're gonna move to the water quantity and water quality that my colleague Clarice gonna present uh, during her presentation. Clarice, the floor is yours.
Yeah, thank you, Miriam. Give me like a small minute to share my screen. Can you all see my screen?
Yes.
Nice, okay. Thank you so much, Miriam, to provide this useful information about hydrology, which tell us how water moves. So here I comes in talking about what that water carries in it. So water quality basic is how suitable the water it is for its intended use. For example, the water quality for drinking purpose might be different from water quality of what we use for irrigation or swimming or water quality that is supposed to support aquatic ecosystem. So simply water quality is suitable, how suitable the water is used. So I will start by just showing you this real life example of water quality issue. As we can see on this slide, we all see murky water and dead fish floating on the top of the river, and some of you might be wondering what happened. So this is one case that shows a real water pollution that later cause harm to fishes. So in this case, in this liver, there was a fertilizer contamination that were released in a liver, and some high concentration of ammonium killed the fish. So not only this example, because we don't use only water for aquatic organisms, but also, as we know that some rivers, lake, or other aquatic ecosystem are used for recreation. So most people use them for swimming, fishing, tourism, and this is an example of Lake Erie, where it provides a very beautiful view, relaxing scenario where most of us, I know that will be happy by now to be sitting on this lake, enjoying the nature. But this was a condition before, and this next image, which was released just this week, last week, it shows how this lake was also contaminated because of algal bloom. So algal bloom is a condition where when there's a high nutrients in water bodies, they accumulate and then cause those algal to grow, and then it causes this issue called eutrophication. So when these things happen, we can clearly see that no one will be enjoy this view. No one want to go to the lake or beach and then see this kind of view. So obviously, this is something that can be defined as bad water quality, but how to understand those changes occurring, we have to measure different characteristics of water. So we can't just sit and observe and tell ourselves what is happening without doing some assessment of key parameters that defines water quality. So we usually assess water quality through three main groups, which are physical, chemical, and biological. And all these groups, they interact each other. And if one of them is compromised, then the whole water quality is bad, because physical, chemical can simply influence what the biological condition. So in that case, all these three physical, chemical, biological parameters goes in hands to define the good water quality. So when you look at the physical parameters, those are the parameters that we can directly observe or measure. For example, temperature, light, turbidity, or sediment. So temperature is simply to tell how hot or warm water it is, and that has an effect on how the water is holding oxygen. And for example, turbidity shows how cloudy is the water, and that is mostly depend on the sediments. When you have high sediments into water and then it causes the water to be cloudy, then it doesn't allow the light to penetrate. And from the basic science, we know that all aquatic, for example, aquatic plants need light to do photosynthesis. So when those plants are not able to do photosynthesis, they die. So looking for the chemical parameters, then those are the chemical substances that are dissolved in water that we can quickly observe, but we can measure them. So for example, pH shows how basic or acidic the water it is, and each organism have the tolerance of that pH. And dissolved oxygen is used mostly to know how the breathing of any aquatic ecosystem can happen. And we know that nutrients such as phosphorus, nitrogen, or other organic matter all support plants, but excess of it also become an issue. So the last parameter, they are called biological, which are like living organisms living into the water, and this includes like aquatic plants, algae, fish, microinvertebrates, and microbes. So because these organisms respond to to physical and chemical characteristics of water, their absence or presence or abundance show whether that water can support healthy ecosystem. So many of those water quality parameters are mostly influenced by what is happening in the surrounding watersheds. As Miriam mentioned, we have seen the structure of watershed, and all this start from the rainfall. When it rains, we know very well that we have runoff coming, and all those runoff comes with a lot of pollutants such as fertilizers and manure from the farmland, sediments, some oil and metal from loads and parking loads, some pet waste and all chemicals that were taken to the lawn, and then some storm water from urban surface. So these non-point sources, they are sources that are scattered and that are not easily identifiable, while we have some point source which are clearly identifiable locations such as a known wastewater pipe or industrial discharge or storm water outflow, and it directly release those pollutants. So this one, they are a little bit easier to manage because we know where they are coming from. So to take the action is mostly easier than managing non-point source. So far we have seen how good or poor water quality look like, and we have just briefly talked about some parameters that we use to get those information. So the purpose of this is to use those parameters, those observations, to make some smart environmental decisions. So we start by observing, and then once we observe, we take measurement, and then we analyze, and then we decide or make actions. So, for example, here in US, we all know Environmental Protection Agency and other government institutions that usually have monitoring programs that are in place already, and such kind of monitoring program help to understand what is going on in our environment, and then they organize the correction and water quality and environmental condition, and they correct data on defined period, and then they analyze, and then they tell what is going on, and then they provide information whether the water quality standards are met or not, and if we are not met, then what is the action to be taken. However, those monitoring program all start with sampling design, and two important considerations here are the time and location. So, for example, we need to know the time that we are sampling at. So we usually do grab sampling, which can be on specified interval like monthly, weekly, or by monthly. And this is good for long-term trends, but might miss some short-term trends because there's a missed interval in between. And nowadays, there are a very good development on how sampling is done by using continuous sensors. So these sensors are installed on your sampling site, and then they can take like daily measurement, which help to detect small changes within the time. Apart from timing, also location matters, where, for example, we need to understand what is how the water quality is from upstream to downstream location, or even midstream location. So here it helps us to understand how is the quality is in spaces. And there's also another way we usually call it hot moment, where we look at storm event sampling, for example, when it rains, and then we need to understand that specific event, the effect of it. And most of the time during the storm event, that is when most of runoff comes with a very huge amount of pollutants. So in that case, some monitoring program can be designed to just capture that storm events that happened in a specified period. So once we do those sampling, then we have to interpret what the measurement and what it tells us. Most of water quality results are often reported as concentration, which is the amount of pollutant in a given volume of water. And here it tells the specific amount of that pollutant in that time and location, specified location. But I would like to introduce also another key metric here, which is called load, which define how much pollutant the river carries. And this load, it combines concentration with discharge. If you remember where Miriam mentioned something like discharge or river flow. So discharge tells us how water moves. So in this case, that is where the water quality and the hydrology become together and become an important tool for making smarter decision. Because even if we understand what is in water, if we don't understand how it's moving, then we are not doing right thing. So mathematically, what I'm saying here is that we usually for water quality have concentration which is expressed in milligram per liter, and once we have these key hydrological parameters called discharge or river flow, then it tells us amount of water in specific time, and then once we multiply those one, we get a load which is mass over unit of time. So simply the load tells us how much portant is being transported by a river for a certain period. To see that well in watershed scale, for example, let's assume that these are upstream site and tributaries, and we are taking samples all the way in those small tributaries, and the concentration, for example, is good, like is below the threshold range of specified portant. But if these concentration keep accumulating, and depending on how much water is moving downstream, we might find that by the time this water reaches in this downstream part, it has like the concentration and the load has increased. So we might start seeing some effect of that pollutant here, even if the concentration upstream is small. So that is why we need both concentration and load to understand or to have a better view of what is being carried. So those values, then we have seen them, we have made measurements. So how do we move from the measurement to the evidence, which is the evidence that help us to detect the issue, and then see the evidence source, and then also take some decisions. So as I said, we start with observation from the field of any pollutants, for example, nutrients, discharge, dissolved oxygen. And the second thing we do is to observe the pattern in or changes over time and space. For example, we can start looking how concentration behave over time, and we can see different trends and patterns where we can see some peaks and some decrease in concentration, and we can relate that with hydrology, and we can see that concentration was just normal, and then at specific storm event, then it has gone up, and then it has come down as the storm has ended. Also, we can see those both behaviors described above, both upstream and downstream. So here concentration can tell you a very good story, but as I said again, in some cases we want also to understand how much in total those pollutants are reaching to our downstream. So that is where we still need hydrology again, as I said. And then once we get the load, then you start matching your observations in concentration and load with source evidence. You might think that maybe the load is due to wastewater discharge, agricultural runoff, road runoff, or groundwater pathway. For example, here I can give an example that is very common here in north temperate watersheds, where we have a very serious winter. During winter, we know that our cities put salt in the roads to cause the snow melt. So when that snow is melting, it also melts together with the salt, and the salt is made by sodium chloride. So for example, you can then, let's say your chloride is your pollutant that you are trying to track. So you might see that at the end of the day, you see the high chloride concentration and load after a snow melt, and in an area which is urban. So in that case, you can relate that high concentration or high load from the road or urban areas. So in that case, we have moved from looking those low measurements, we have looked at the pattern, we have been able to identify the source or evidences of where the potential pollutant is coming from. And then from that, we can give some decision based on the source. However, not every monitoring program provides the same amount of information. For example, how confident we are in those those decisions mostly depend on how confident we are in our monitoring design. For example, we can say that we have high confidence when we have a watershed and we have a good representative of sampling station which capture all part of the watershed, like from small tributaries in the middle reach of the watershed and then up to downstream. So once you have frequent sampling, multiple site and flow data is included, which is hydrological data, then you can confidently say that whatever decision you have come up with is well grounded with what you observed on the field. But moderate confidence is also possible where you just have like just few representation of your data for your watersheds, and you have some small gap, limited site, partial source information. And for example, in this part, we see that we have just like 3 sites, which is upstream, mid, and downstream, but we don't really know what is happening or from the other part of the watersheds. And then we also call low confidence when you have like very limited sampling site, for example, one site within this whole big watersheds, and you don't have other corresponding flow data or or anything. So I can say that the decision that we will make here might not be well present, might not present well what is going on. So all these confidence also have some parameters or have some controlling factors, such as low costs, because most of the time all these frequent sampling, multiple site, all depend on how is your budget to set up a lot of site. All those goes with a lot of logistics, like staffing, instrument, lab work, and also in some cases we have some remote areas where, for example, where there is no accessible sites for people to go to the field. So in those cases, then that is when Miriam said like some remote sensing and satellites comes in and help also to cover that gap. Yeah, so before I finish my talk, then I would like to go on a very real case study that shows how they moved from the problem to the solution. And here is an example of Tampa Bay in Florida. So Tampa Bay in 1950s, as you can see here on this graph, we see seagrass coverage. So seagrass is an aquatic plant that is that is that lives underwater, and it provides habitat for fishes and other small microinvertebrates in water, and this seagrass help to reduce sediment. So it's really considered as a very good indicator of healthy ecosystem. But in this Tampa Bay, what happened in 1950s, which they mark as their reference period, we see that the coverage of this seagrass or plantation was good and high, but over time it started reducing dramatically, and around 1982 it has almost decreased up to half. So they monitored and they found out that there was a high nitrogen pollution effect because of increase in populations and increase in agricultural runoff, and there was no treatment plant that treat human waste. So all that contributed to the decrease of seagrass coverage. So when they saw that, a lot of agencies and came together and started planning how they can reduce this nitrogen pollution and come up on a sustainable solution. So they started by regulating the nitrogen release, and they upgraded their water treatment plants, and then they also regulated some detergent that release phosphorus, which is same as nitrogen, that all cause the pollution. Then they continued the monitoring after that. So they wanted to know if those management action actually improved the condition of the bay. So that is when they used the long-term monitoring data to answer those questions. So we can see that after sometimes in 1987, the seagrass again started coverage started going up, and we can see that in the recent years, like around 2014 till now, the seagrass coverage has gone up, and it has even passed the reference condition that was there in 1950. So they can confidently say that those management action did a great job. But also, they did not only monitor or evaluate the success of this, they also used other parameters called chlorophyll A to see if it really worked. So chlorophyll A is the amount of green pigment that is available for all photosynthetic plants, and it is a good indicator as it indicates amount of algae that is available in water. So when chlorophyll A is high, means that also the algae is high. So we can equally see that in area years in 1975, chlorophyll A was high, which means that there was too much algae. But as time goes, the chlorophyll A started going down, and then it has, even now, these recent years now, it has gone down up below to the management target. So these blue lines you see here, they are management target that I have set. So we can easily see that around 2017 up to 2025, in all these monitored sites, the chlorophyll air values are below the management target. So we can see that this has been a success, but we can imagine how long term this monitoring has started, because it has started in 1882, so almost 50 years. So this is an example that shows us how hydrology and water quality work together to influence the decision that we make. So I hope in this presentation we are able to touch on some of your questions that have been wondering how this can help to make an environmental decision. And this is the end of our presentation. So we'd like to welcome any comment, discussion, or ideas. So thank you so much.
Yeah, we have one question. Let me
Okay.
from from James. Let me bring him to the stage.
Okay.
Okay, hello. Thank you
Hello,
so
Jen.
much
Hello.
for this wonderful session. I have a question about a part of the workflow for hydrology or water quality mapping, and it has to do with calibration. Um, do you think it's such an important process? Is it something that we should discard moving towards the future, or it's really important and it should be something that should be critical for the workflow of creating these physics-based observation models?
Yeah, well, thank you for your question. The calibration is a very important component of hydrological modeling. I don't know in which topic you're working right now. Like, are you doing hydrological modeling
Floods.
or?
I do it in flood modeling. Yeah.
Okay, so we're in the same topic, flood modeling. If you, with which model you are working on? right now? Like conceptual model, based physics model, machine learning model? Which kind of model you are using?
I'm inclined towards machine learning models right now.
Mhm. Okay, so for machine learning models, there is like um, let's say automatical calibration. It's not like a physics-based model that you can do it manually or do it like automatically. You can choose, but for the machine learning one, you can only write a script with the calibration parameter that you want to use depends on your data and the outputs that you are expecting to have, and then like the script do it itself, you know. However, if you want to use based physical model or conceptual model or so on, your since it's application in a platform, so you have to respect the calibration parameter to calculate each parameter using the equation, and then like not only estimating the calibration parameter, you know. I don't know if I answered your question.
Yeah, that kind of solidifies my thinking that calibration is very important. Um,
Yeah,
yeah, thank you.
you're welcome.
We still have some minutes for more questions, so feel free to drop a message or raise your hand if you have anything to add or say. I think
Yeah,
Larissa
there is
has, yeah, you can bring her on the stage.
done. My text, yeah.
Larissa, we can't hear you. Okay, I think she's typing on the chat.
Okay.
Yeah, you can drop your question here in the comment, then we will read it and respond to it. Yeah.
Hello, can you hear me now?
Yes.
Hey,
Oh, you are gone again.
Yeah, she's back.
Okay.
Let me bring her to the stage.
hello.
Yes.
Larissa,
Hello.
could you hear us?
Yes, I can hear you. There is
Perfect.
a little problem with the camera, so hang with me. Sorry about that. No video, but audio.
No
Okay.
worry.
So I do have. Thank you very much for the explanation, both of you. I do have two questions, more likely curiosity question. As my background is in oceanography and environmental study, let's say that. One question is, I saw that in the part of measurement, uh, um, quality assessment, that is a part of where you say it's a moderate or it's more in the precision of the measurement. Uh, what metric, how much you would say it's a good spatial coverage of measurement station to tell if it's sparse, if it's moderate, or if it's a good, accurate or trustful measurement data
Okay.
set. Let's say.
Okay. Thank you so much for a good question. I think as what I meant there is that I wanted to say that I think all depend on your interest, your parameter interest, because some of them respond quickly with time and space, and other do not respond. So I think all depend on the parameter of interest and also the reason. For example, I can give a simple reason. When I presented, I talked about chlorine, for example. So if my monitoring purpose is to look at chloride concentration or rods, there are some hot moments or hot spot that I can't miss. So for instance, here I mean if I know, it also has something to do with the literature and what you know about of that specific pollutant. For example, if I know that chloride is more likely to come from snow melt, and during winter if they have put salt, and then if it melts, then I'm probably sure that that will be the right time to measure that pollutant. So in my monitoring design, I will do whatever is possible to not miss that winter session. So that is one example. And also another example I can give is, for example, let's say for nitrate, which is an issue for agriculture. So I'm just giving an example here in North Temperate. We know that growing season starts spring, summer. That is when farmers cultivate and apply fertilizers in their field. So if I'm trying to monitor nitrogen, then I will try not to miss that seasons, because that is mostly when I will likely see the big change, because that is when the farmers are applying for nitrate, and also that is when we are having heavy rains that will probably have storm, and then that will carry on those nitrogen. So simply I would answer that by just saying that we can just first look at the pollutant that you are trying to study, and then have some background information on it, and know probably what will be the major source of this, what will be the most good timing of this, and then design your monitoring or sampling based on that. But as I said, as most of the time cost is an issue. So when you are designing, if it's a long-term trend that you want to look, or if it's a hot moment, or like a specified period of time you want to look at, then you should first focus on what is mostly likely to bring the changes in this concentration of this specific pollutant. So I think that is how I can answer that. Otherwise, it's really hard to say like we will have enough enough materials, or enough materials to to track that pollutant like every day, every time for the whole year. So it all depend on the pollutant that you want to study, and also try to understand in advance like what will be the major space and time that things will appear most. Yeah, I don't know if I have covered everything that you asked.
Yeah, no, it sounds fair. It's more complicated than
Yeah.
it seems. So,
Yeah.
another question I had, and it's also a curiosity one, and I was curious to know if you have studied or know of study cases or examples of alternative uses, for example, for pluvial runoff or water resources that sometimes is polluted, like the example you gave for the algae bloom on the Erie Lake. If you study we study if you study that, or if you know about this, because for example there is one example here in my state. They used the water from a lake where they have a strong algae bloom, and they use this water for as a fertilizer, so they spray in a field for the grass, was for cattle. um,
Mm.
I don't know about study and papers that kind of reinforce this use, and I was curious if you know an example like this, or pluvial runoff. It can be algae bloom or any case.
Uh, okay, thank you for sharing that. I don't think I really know a very specific example like yours, but and for my own research, I'm like generally studying how nitrogen move in the watershed, and here in New Hampshire, I just study like tributaries that drains into Great Bay. So I usually use some existing data from USGS and available data sets, water quality available from New Hampshire Department of Environmental Services. So I'm not doing any field measurement or any data correction, but I just use like existing data and trying to understand or estimate those loads and relate it to land use change, and also inform the management what they can do, because I try to track the nitrogen pollution from different sources, like from agriculture, from atmospheric position, from human waste. So I don't really deal with a lot of data correction right now, but that is a good example, and maybe I can follow up and see if we can look together and see some interesting studies that are doing like what you described.
Thank you, thank you.
Thank you.
Yeah, we have another question. Let me go. From Fatima. Let me bring her to
Okay.
the stage.
Hi, can you hear me?
Yes.
Yes, we can.
Okay. I was thinking that, like you mentioned, we have gaps in terms of hydrological modeling or something like that. I think that's the question from both perspective, whether we are doing the watershed modeling like rainfall, runoff, or we are trying to see the contaminants like contaminants or nutrients, like we are trying to follow the pathway of anything that is describing water quality. So is it possible like the data gaps can have the bigger issue, like how we are filling the gaps where we don't have enough data?
Can I start with that? Okay. Yeah, I will talk on water quality perspective, and maybe Miriam can add something on hydrology. But as you said, there's
Exactly.
a very serious issue of data gap, and most of the time that is when modeling perspective comes in, because there are a lot of models in water quality studies that, for example, I mentioned like grab monthly sampling. So you can imagine if you are sampling once a month, and that data will be the whole representation of the whole month. Eh, Obviously, we will miss something somewhere, because all days are not the same, and then you might capture that measurement when there's no rain, and then the next day it is raining, and then there'll be a different story. So to simply say that, what we usually do is to rely mostly on those models that try to use the few samples or few measurements that we have, and then try to simulate or try to predict what will be like the measurement for all other missed days or periods. And then I think that also brings back the GEMS issues on calibration, because whatever I do with those models, then we have to calibrate. So I think we usually use models, and then if you are lucky enough, your models predict well, and you have the confidence to say that these models, whatever is doing, is a good representation of the real ecosystem, and then you can use those data to fill the gap of what you are doing, which I think works the same way for hydrology, but I will let Miriam add something since she's the an expert in hydrology.
Thank you, Clarice, for your insightful information. And thank you, Fatima, for this question. Well, I will talk on the hydrological way. When we have a gap of data, what we're trying to do is to fill that gap. So first thing first, we go to satellite or remote sensing data. We took some satellite product, compare them with the observed one, and calculate the bias, correct this bias, and then calibrated the model with the observed one with that gap, then also do another calibration with the remote sensing data without gap and compare between both of them. If we reach like a fair NSE, or depends on the statistical like metrics you want to use as a hydrology as the
Mm,
hydrologists we usually use NSE. So if the NSE are comparable or good, we can take the satellite data to fill. We can fill like the gap with the satellite data, and then
mm,
do another calibration. Since we're trusting the satellite one, we did the correction, the bias correction, like and everything. Then we could use those data to fill the gaps. This is an option. Another option is to using machine learning and like LSTM and so on to fill those gaps. Like the output of the machine learning model gonna be the, the, the data that you could fill the gap with. And also like you could also use some models, try to calibrate your model with the input data as they are with that gap, got the final output, and then try to reconstruct that historic gap that you have. But I'm
mm.
only encouraging you like to use the first one, using satellite data, correcting the bias and calibration with both ways, and cooking those data to fill in the observed gap. Yeah.
Yeah, because I was thinking that at least for hydrological simulations, we have satellite data as a backup. Like we can use it to train our models and to fill the gaps. But where the existing sampling is going on, like we take sample for groundwater contamination, but sometimes we don't have data for certain sites, and then we don't have even data from satellites. So, is it possible that we can also have some suggestions for those kind of gaps?
Yeah, like machine learning could
Mm,
eventually found
yeah,
solution for that gaps. Can use like
yeah,
LSTM or random forest or XGBoost. Then like got the output and fill
yeah,
the gap
yeah,
with those outputs. Yeah,
yeah, perfect. Yeah, that's insightful. Thank you. Thank you.
Welcome.
you're welcome. Is there
Mm,
any question?
checking the comments. Seems like no more comments or questions. So I think that's all. Uh, yeah, no more comments.
Yeah. If there is no more comment, we can stop recording and then finish this workshop.
Yeah.
Yeah, well, thank you so much for being here today and joining us for this workshop. And I'm very glad to share this session with Clarice, and wishing a very good success to LabLinks for their upcoming workshops. And yeah, happy to be there. Thank you so much. Bye bye.
Okay, bye. Thank you all. Okay, I think we can end.